Welcome to week 7. We're almost done. This is part A. This week marks a pivotal shift in our course. For the first 6 weeks, we focused on building databases and writing queries and working with healthcare data. But now we return to protecting that data. Database security in healthcare is not a nice to have. It's a federal mandate. It's under the HIPAA law. And the consequences of getting it wrong are measured in millions of dollars and potentially millions of compromised patient records. By the end of this section, you will know how to implement robust access controls in Postgres using the same tools that production healthcare systems rely on. So why does database security matter so much? Well, let me give you some numbers to set the stage for why it matters. As recently as 2024, there were 742 large healthcare data breaches reported to the Office for Civil Rights, the OCR, in the federal government. Those breaches compromised over 276 million records, which represents roughly 81% of the entire U.S. population. The single largest breach was at Change Healthcare, which affected an estimated 190 million individuals and disrupted pharmacy processing and healthcare billing across the country for months. Moving now into the past year, into 2025, we saw approximately 697 breaches affecting around 61 million individuals. And those numbers are still being updated due to reporting delays. So this is not an abstract risk. This is the reality of the industry. So what does this cost? According to IBM's Cost of a Data Breach report, the average healthcare data breach now costs $7.42 million, almost $7.5 million, which is down a little bit from $9.77 million the prior year, almost $10 million. But healthcare still held the #1 spot as the most expensive industry for breaches. It has held this now for 14 consecutive years since they started measuring. Why is it so costly? Well, one reason is the breaches take an average of 279 days, that's almost 9 months, to identify that the breach has occurred and then to contain it, which is more than 5 weeks longer than the global average across other industries. On the dark web, a single stolen medical record is estimated to sell for $260 to $310, roughly 10 times the value of a stolen credit card. Why? Because credit card can be canceled and reissued. A medical record contains your diagnoses, your medications, your social security number, your insurance details. Most of that information never expires and can be used for identity theft and insurance fraud, and can be used in blackmail for many years. So what is the regulation, the HIPAA security rule, the minimum necessary standard? This is a federal law, specifically 45 CFR 164.312. And it requires covered entities, and we'll get into that later, to implement technical safeguards to protect electronic protected health information. Protected health information. We've talked about that a lot. Among the most important requirements is access control, which means ensuring that only authorized persons can access specific health data and only the minimum necessary data for their job function. This maps directly to the CIA triad that you will see in any cybersecurity course, the CIA triad. The first, confidentiality, meaning only authorized users see the data. Integrity, meaning data cannot be altered without authorization. And availability, meaning the data is accessible when needed for patient care. So what we're going to learn today is how to implement these principles technically in Postgres using users, roles, grant, revoke, and row-level security. So let's talk about users and roles. Let's start with the fundamentals. There's an important concept that trips up beginners. A user and a role are essentially the same thing. The difference is that create user is just a shorthand for create role with a login privilege. When you say create role, nurse role, you are creating a group role that cannot log into the database directly. When you say create user Dr. Smith with password, you're creating a role that can log in. The best practice in any healthcare database is to create roles for job functions, but not for individual people. You create a physician role, a nurse role, a billing role, and then you assign individual users to those roles. This way, when a new nurse joins your organization, you simply add them to the nurse role and they automatically inherit all the correct permissions. So how do you do that? What's the syntax? We create our job function roles first. Create role, example, nurse role. Create role, physician role. Create role, billing role. These are group roles with no login authorization. Then, when we onboard an actual user, we say create user, Dr. Smith, for example, with password, followed by a secure password. And we include in role, physician role. This simultaneously creates the user and assigns them to the physician role. You could also do this in 2 steps by creating the user first and then using grant physician role to Dr. Smith. Both approaches achieve the exact same result. Well, roles can be organized into hierarchies using inheritance. By default, when a user is a member of a role, they inherit that role's privileges, and this is controlled by the inherit attribute. You can also nest roles. For example, you might create a clinical staff role and then grant both physician role and nurse role membership in the clinical staff role. Now, any privilege granted to clinical staff role automatically flows down to all the physicians and nurses. And this mirrors how healthcare organizations actually structure their access. There are permissions common to all clinical staff, and then more specific permissions for each job function. And the key thing to remember is that the role hierarchies reduce administrative burdens. When you need to change what all clinical staff can access, you change it once at the clinical staff level role, but it propagates to everyone. Okay, let's look at how we actually implement this. Now that we have users and roles, we need to give them permissions. This is where grant comes in. The syntax is straightforward. Grant, and then list of privilege, on, and then a specific object, to, and whatever the role you want to incorporate. The most common privileges are select, insert, update, and delete. So those are the privileges we want to assign, which correspond to reading data, adding new rows, modifying existing rows, and even removing rows. You can also grant all, which includes all of these. The objects you grant access to can be tables, schemas, databases, or sequences. In a healthcare context, you're very deliberate about who gets which privilege on which table. A nurse might get select and insert on vitals because they need to read and record vital signs, but they should not have delete because you never want vital sign records disappearing from the system. Let me show you what this looks like for our X-Health database. We grant physicians select access on patients, encounters, and diagnosis because they need to review the full clinical picture. We grant nurses select, insert, and update on vitals because recording and updating vital signs is a core nursing function. We grant the billing role select on diagnosis so they can access ICD-10 codes for billing purposes, but we do not give them access to clinical notes or medication details because that violates the minimum necessary principle. And critically, we revoke all on patients from public. In Postgres, public is a special role that includes everyone. And by revoking from public, first we ensure that no one has access unless we explicitly grant it. This is the principle of least privilege and is foundational to healthcare database security. Postgres gives you even finer control than table permissions. You can grant access to specific columns within a table. This is extremely useful in healthcare. Consider the billing staff. They need to see patient ID, first name, last name, and insurance ID to process claims, but they should never see clinical notes, diagnoses, or medication history. So with column level grant, you can say grant select on only those 4 columns of the patient table. 2, the billing role. When billing staff query the patient's table, they will only see those 4 columns. If they try to select a column they do not have access to, Postgres will return a permission denied error. And this is the minimum necessary standard in action at the column level. Revoke is the counterpart to grant. The system mirrors grant. The syntax mirrors grant. Revoke a specific privilege on an object from a given role. One important nuance, revoke does not create a deny rule. It simply removes a previously granted permission. If a role was never granted a privilege in the first place, revoking has no effect. Postgres operates on a default deny model. If you enable role-level security or set up your roles properly, users have zero access unless something is explicitly granted. This is the secure by default approach that HIPAA expects. Granting and revoking privileges is only half of the story. You also need to audit who has access to what. HIPAA requires periodic access reviews. In Postgres, you can use the \dp command to see all privileges on tables. And programmatically, you can query the information, schema, row, table, grants. All right, that's a specific built-in function. You get this view to be able to get a comprehensive list of who has what access on which table. This is the query you would run before a HIPAA audit to verify that your access controls match your organization's access policies. If you find a discrepancy, say a billing clerk who has update privileges on the medication table, you revoke it immediately and document the correction. All right, here's a big policy, the role-based access control, RBAC, role-based access control. We control access based on the role. So now that we've set up the concept of role-based access, everything we just covered with grant and revoke is the mechanism to accomplish this. Role-based access control is the strategy. The core idea is quite simple. Access is determined by job function, not by an individual's identity. Instead of saying Dr. Smith can read the patient table, you say the physician role can read the patient's table, and Dr. Smith is a physician. This is a critical distinction because it makes your security model scalable and auditable. When someone changes job functions, you reassign their role rather than individually modifying dozens of permissions. And when an auditor asks who can access patient records, you can answer at the role level rather than listing hundreds of individual users. So role-based access control maps directly to HIPAA's minimum necessary standard. because each role is designated to have exactly the access needed for that job, and no more and no less. Well, let's design a role-based access control model for our xHealth database. We start by identifying the job functions: physician, nurse, billing clerk, lab technician, database administrator. Then we map each function to the data access it requires. For example, physicians need read and write access to most clinical tables because they document encounters, write diagnoses, prescribe medications. Nurses need read access to most clinical data, but write access primarily to vitals and encounters. Billing staff need read access to limited columns on patients and read access to diagnoses for the ICD-10 codes, plus read-write on insurance. Lab technicians need read access to limited patient demographics and read-write on vitals for entering lab date results that go in the vitals table. The administrator has full access for database maintenance. This table becomes your security blueprint. You implement it with create role and grant statements, and you reference it during your HIPAA audits to demonstrate your compliance. So here's the full SQL implementation for xHealth. We create a clinical staff role as a parent, then physician role and nurse role as children. And we use grant to assign specific privileges on each table to each role. The code might look a lot like a lot of SQL statements, but each one maps directly to a call in the access matrix we just designed. And this is the kind of setup you would do once when deploying a healthcare database, and then maintain as job functions evolve. The important thing is that this is all auditable and documented. Every grant statement is a decision that ties back to a business requirement and a HIPAA compliant justification. Let's walk through a real scenario. A new nurse named Maria joins xHealth. Step 1, the database administrator creates her user with create user Maria with and specifies her password and assigns her to nurse role. Step 2, Maria logs in and automatically inherits all nurse role privileges. She does not need any additional configuration. Step 3, Maria tries to query the insurance table. Well, Postgres returns permission denied because nurse role was never granted access to insurance. And step 4, Maria inserts a new vital record for her patient and succeeds because nurse role has insert privileges on the vitals table. And this is how role-based access control works in actual practice. The administrator did one thing: assign Maria to a role, and all the correct permissions were automatically in place. Role-based access control is powerful, but it has a fundamental limitation. It controls access at the table level. Can you access this table? Yes or no? And with what operations? But what if we need something more granular? Consider this. Dr. Smith and Dr. Jones are both physicians. Both have select access to the patients table, but should Dr. Smith be able to see Dr. Jones' patients? In many clinical settings, the answer is no. A physician should only see patients assigned to them. Role-based access control alone cannot enforce that because both doctors have the same role with the same table-level privileges. So we need a mechanism that filters individual rows based on who is asking. That mechanism is called row-level security, RLS. Row-level security is one of Postgres' most powerful features for healthcare applications. While role-based access control answers the question, can you access this table? Row-level security answers the question, which rows in the table can you actually see? Think of it as an automatic invisible where clause that Postgres adds to every query. When Dr. Smith runs select star from patients, Postgres silently, behind the scenes, appends a where primary physician ID equals Dr. Smith, so only Dr. Smith's patients are returned. Dr. Smith never even knows the filter is there. From their perspective, the table only contains their patients. This prevents what security professionals call bulk data snooping, where an authorized user with table access queries far more data than they need. So row-level security is a core defense against internal data breaches, which are a significant problem in healthcare. Well, enabling row-level security requires two steps. First, you alter the table to enable row-level security with the statement alter table, and then in this case patients, enable row-level security. And then second, you define one or more policies using create policy. This order matters. Once you enable row-level security on a table with no policies defined, Postgres defaults to deny all posture. No rows will be visible to anyone except super users and the table owner. Now, super users bypass row-level security by default, which makes sense for a database administrator. But if you want even the table owner to be subject to row-level security, you use alter table patients force row-level security. In a healthcare setting, you would typically enable row-level security and then immediately create your policies before any end users attempt to query the table. All right, here's the syntax, the create policy syntax. It has several components. You give the policy a name, specify which table it applies to, and optionally specify which SQL command it applies to, such as the four common ones, select, insert, update, delete, or all, and optionally specify which role it applies to, and then define one or two Boolean expressions. The using clause filters which existing rows the role can see. Think of it as the read filter. The with check clause validates whether a new or modified row is allowed. Think of it as a write filter. If you only specify using, Postgres applies the same expression to with check as well. This means a doctor who can only see their own patients also cannot insert records to another doctor for another doctor's patients. So here's the healthcare example. We create a policy called doctor-owned patients on the patients table for select operations applied to the physician role with a using clause that checks whether the primary physician ID equals the current user. The current user function in Postgres returns the username of the person running the query. So when Dr. Smith runs select star from patients, Postgres internally rewrites this as a select star from patients where primary physician ID equals Dr. Smith. Only Dr. Smith's patients are returned. If Dr. Jones runs the same query, they get only their patients. Same table, same rules, same SQL statement, but different outcomes, different output, different results based on the user's identity. This is incredibly powerful for healthcare compliance. Row-level security policies can be more sophisticated than simple user matching. Look at this example. We create a policy for nurses that uses both a status check and a session variable. The using clause requires that the encounter status is active and that the department matches a session variable called app.department. Session variables are set by the application when the user logs in. So, a nurse working in pediatrics would have their session variables set to pediatrics, and they would only see active encounters in the pediatrics department. This demonstrates how row-level security can enforce context-aware security, restricting access not just based on who you are, but based on where you are working right now. So what happens when you have multiple policies on the same table? Postgres distinguishes between permissive and restrictive policies. Permissive policies, which are the default, are combined with OR logic. If a user matches any permissive policy, they get access to that row. And this is useful for expanding access. For example, a doctor can see patients where they are, the primary physician, or where they are also listed as the consulting physician. Restrictive policies are combined with an AND logic, not OR. All restrictive policies must be satisfied for a row to be visible. This is useful for adding additional constraints. For example, a permissive policy grants access to a doctor's patients, but a restrictive policy additionally requires that the patient record is not flagged as sealed or restricted. The combination of permissive and restrictive policy gives you very fine-grained control. All right, let's step back a minute and see how all of these security layers fit together. Layer 1 is authentication. Who are you? This is the Postgres login with username and password. Layer 2 is role-based. Role-based access control through GRANT and REVOKE. What tables can you access? Then layer 3 is the row-level security, which is delivered through create policy. Which rows within those tables can you see? And finally, layer 4 is column level. Column level privileges which columns within those rows are visible to you. So each layer narrows the data further. A billing clerk authenticates. Row-based access control gives them select on patients, but column level privileges restrict them to 4 columns. And the row level security could further restrict them to patients within their assigned facility. So this layered approach is what security professionals call defense in depth, and is exactly what HIPAA expects when it says to implement technical safeguards. All right, now we're going to expand to the big picture in the industry. Everything we've discussed so far secures data at rest inside the Postgres database. But in a modern healthcare system, data also moves between systems through APIs. And this is where Smart on FHIR comes in. What does that mean? SMART stands for Substitutable Medical Applications and Reusable Technologies. And it is built on top of OAuth 2.0 and OpenID Connect. Smart on FHIR defines scopes, which are essentially row-based access control for API access. A scope like patient/observation.read means an application can read observation resources for a specific patient. A scope like user/encounter.rs means a clinician-facing application can read and search encounter resources that the logged-in clinician has access to. There are 3 levels: patient scopes for single patient contexts, user scopes for clinician-level access, and system scopes for back-end services. The newest version, Smart on FHIR v2, even supports granular filtering within scopes, like restricting observations to only laboratory category results. Well, here are the key connections. Database security with Postgres, roles GRANT, REVOKE, and row-level security protects data at rest inside the database. Smart on FHIR scopes protect data in transit as it moves through APIs between different systems. Both implement the same fundamental principles: minimal necessary access. A complete healthcare security architecture requires both layers working together. The database ensures that even if someone bypasses the API layers, the data is still protected. The API layer ensures that external applications only receive the data they are authorized to access. This connects directly to what you learned in weeks 4 and 5 about FHIR and the US CDI. Those weeks covered the format and content of healthcare data exchange. This week, we're adding the security layer on top. Let's recap what we covered. Database security in healthcare is not optional. It's mandated by law, by HIPAA, and the consequences of failure are severe. Postgres gives us robust tools, users and roles for identity management, GRANT and REVOKE for table and column level access control, and row level security for row level filtering. Row-based access control maps job functions to data access, making your security model scalable and auditable. Row-level security adds granular row-level control that prevents internal data snooping. And Smart on FHIR extends these same principles to the API layer for interoperability. In your security lab, your homework this week, you'll put all this into practice by configuring roles and row-level security policies for our X-Health